We will move towards the proof of the key theorem actually. Okay, so let me quickly state the theorem that I mentioned in the first video of today's discussion, which says that if the U naught is from H, which is H2 intersection H1 naught, then for every such U naught you can find a smooth function of space variables that satisfies what do you call the stationary version of the problem. In other words, it's an equilibrium point. It's a stationary solution of the problem star, the reaction diffusion equation that we are interested in, such that the solution of star, whereby star I mean reaction diffusion equation that I introduced in the first part of the video, first part of today's discussion, star U, for which this U you have this actually. Okay, so there is solution U of star converges psi in H as t goes to infinity. That is, if you compute the H norm of U at t and subtract, say, psi in H norm, this will go to 0 as t goes to infinity. Okay, so this is what really is the key result. For the sake of record, okay, let's also put let's just start proving this result. As I said that, you know, if we have the Hager-Wightman inequality, we can prove this inequality. So how we can do it? So the first step is really, we're going to do it in, basically we can do it in several steps. So the first step is to quickly recall that we know about the problem star. Okay, we know that solution U star is a gradient flow actually. Is a gradient flow that is this H2 intersection H1 naught S of t, and T is a gradient system. So we proved it in our last class that this is a gradient system. And we know that about the gradient system, if you consider the initial condition from, say, H2 intersection H1 naught, okay, then the omega limit set corresponding to the, say, initial condition U naught consists of, so it consists of, what do you call, size, okay, that satisfy, for example, this stationary solution actually, okay. So it consists of size that satisfy, okay, stationary solution, which is kind of a stationary solution of nonlinear reaction diffusion equation that we are interested in actually. Okay, and we also deduced actually, we can deduce from our discussion in the last lecture that there is a sequence Tn that explodes as n goes to infinity, and if you evaluate your solution at, what do you call, U at this sequence Utn, it will converge to you call psi in H as n goes to infinity. Okay. So this is a conclusion that we already know from our last discussion, last lecture actually, that since this is a gradient system, for the gradient system omega limit sets consist of such equilibriums are the, what do you call, stationary solutions of your nonlinear evolution equation, and the psi that belong to the omega limit set has the property that for them there exists a sequence ut tn as tn goes to infinity, such that u sitting on these tn approaches to psi in H norm as n goes to infinity. So this is a conclusion that you have. So what is the step 2? Step 2 is really starts with, for example, this observation that you know the relation. So in other words, the energy of the system star. Okay, so its energy satisfies this relation. We derived this relation in our last class. E of u of t plus it's equal to minus time derivative of it square actually. So it satisfies this inequality. You can reduce this inequality easily by, for example, multiplying the equation star, the reaction diffusion equation by ut and integrating with respect to x actually. So we reduced it last time. You can see the details in our last lecture actually. And this shows that, you know, the energy of the system is dissipative actually. Okay, so since the energy of the system is decreasing, okay, since the energy of the system is decreasing, so you can say actually, so E is decreasing in T. Okay, so for all t bigger than or equal to 0, you have this conclusion that the E evaluated at u of t, the difference of E evaluated at u of t and E evaluated at a stationary solution psi must be bigger than or equal to 0. This must be, what do you call, bigger than or equal to 0. Now, we will show that if E of u of t is equal to E of psi for some instant, you have your required conclusion, in other words, this convergence. And if E of u of t is strictly bigger than E of psi, you still have that conclusion actually. So let's start with, for example, the simple case for which we say that imagine there is an instant t naught, okay, bigger than or equal to 0, such that the E of u of t naught is equal to E of u of t. Okay, so E of u of t naught equal to E of psi. Okay, so there is a t naught. So since this quantity can be equal to E of psi, or this can be strictly bigger to E of psi, in both cases I want to show that this conclusion holds. So I'm considering the first case, that simple case, that when E of u epsilon naught is really equal to E of psi, okay, for some instant t naught. Now if this is the case, then this equation also holds for, what do you call, instant t equal to t naught. Or you can say for any t bigger than or equal to t naught, okay, since E of u of t naught is, so if E of u of t naught is equal to psi and t is instant after, what do you call, t naught, then E of u of t would still be E of psi actually. And if I take that E of u of t equal to psi and substitute it into this equation, then since E of psi, okay, is time independent, so its time derivative must be 0. Okay, so for t bigger than or equal to t of psi, since E of u of t is equal to E of psi, so if I substitute E of psi here and it computes its time derivative, since this is a stationary, so this must be 0, and hence what follows it follows, what follows that the norm of ut is 0 from this equation, because if this is 0, the norm of ut square is 0, norm of ut is 0, and ut is equal to constant. And if the ut is equal to what do you call constant, then u must be constant. Ut is 0, then u must be some constant c. And if you know the u at, for example, one instant, okay, if you know the u at one instant, you know it at all instants actually. So you can say actually that your u is constant. So in long run, your u would be precisely equal to psi. It would be precisely equal to psi. Since it is constant, so it must be precisely equal to psi in the future actually. Because I know that u at Tn converges to psi. Okay, so this you have this. Now, if u is precisely equal to psi, then obviously, you know, u at say t minus psi and its h norm, this must be equal to 0. This must be equal to 0 for all time t, and it will be 0 as t goes to infinity. So you have the conclusion of the theorem if u is precisely equal to the psi. The more interesting question is going to be when e of u of t is bigger than or equal to, strictly bigger than or equal to p of psi. So now we will consider the case when p of u of t is strictly bigger than p of psi actually. Okay? This is what is. Then what we can do, so I can rewrite, for example, this equation. Okay, let's call this equation A. So now for t bigger than or equal to 0, let me rewrite the equation A. And how I'm going to rewrite? Let me rewrite, say, d by, say, dt. And I have e of u of t. Let me subtract e of psi. Would that make any difference? This would not make any difference because e of psi is independent of time, so its time derivative must be 0. So this is really equal to d by dt of e of u psi. Okay? Plus, I have ut squared. So let me put one ut and let me put another ut. So ut squared is like norm of ut multiplied by norm of ut. But I know about ut from my equation that it is equal to Laplace u plus u minus u cube. So instead of writing ut square, I'm going to write ut multiplied by, say, Laplace u plus u minus u cube and its norm actually. And this equal to 0. So I haven't changed anything. You have to keep one thing in head that I haven't changed anything. This is precisely the same equation, what do you call A. Let theta be the number between 0 to 1/2 as it appears in what do you call your previous lemma in last lemma. So let's imagine that this is my. Now, if I take, for example, and compute the derivative of, with respect to dt, e of, say, u of t minus e of psi power theta. Okay? So I compute this. So by definition, this is going to be theta times e of u of t minus e of psi. Okay? This is going to be e of psi power theta minus 1 times the derivative of the base actually. Okay? The derivative of the base. And what would be the derivative of the base? So the derivative of this is 0 and you're going to have times the derivative with respect to dt of e of u of t. Okay, this is what that you're going to get. Now, what I can do, or maybe if you wish, you can also keep this term as it is for now, because in this expression you have this term. So probably it would be better to keep. So it's e of u minus e of psi. Okay, this is what is really the conclusion of this. Now, if I use this inequality, this equality here, so what you're going to get? So if I use this equality, if I use this equation here, what you're going to get? That if in this equation, say I substitute the value of say du by dt of derivative of u of t minus e of psi, okay, so if I substitute the value which is going to be the difference of this here, okay, then what you're going to get? What you're going to get? You're going to get this. I'm going to get the d by dt of e of ut minus e of psi power theta. So in this, so this expression would stay as it is, and this would be equal to minus of this actually, minus of this. So I take the minus of this, substitute it here, so you're going to have a minus here. And if I can take this entire term on other side, so you're going to get this. Plus theta times of e of u of t minus e of psi power theta minus 1, okay? Power theta minus 1 times Laplace u plus u minus u cubed multiplied by the norm of ut equal to 0. So this is what that you're going to get actually. So I hope you got this simple calculation actually. Now here is something interesting. In this part, now I would like to use what you call my Hajevic-Thamin inequality. Okay, I want to use my Hajevic-Thamin inequality. So if I apply Hajevic-Thamin inequality by LS inequality, I know that this guy delta u Laplace u plus u minus u cube, its norm is bigger than or equal to e of u minus e of psi power 1 minus theta. Okay? That we have this Hajevic-Thamin inequality. By Hajevic-Thamin inequality, this term is bigger than or equal to, what do you call this term? And if this is the case, then this left hand side, okay, so if this is bigger than or equal to this, then this left hand side of the above equation, which is equal to 0, okay, for now, which is equal to 0, would be bigger than or equal to what? It would be bigger than or equal to d by dt of e of u of t minus u of psi power theta plus, okay, plus theta times e of u of t minus e of psi power theta minus 1, times from this inequality, this is bigger than or equal to this. So in product, you're going to get E of U of t minus E of psi power 1 minus theta times ut. Okay, so in other words, this entire left hand side, which is equal to 0, is bigger than or equal to this one. But if you see carefully, you can get rid of these two terms because they have the opposite powers. So this means theta multiplied by ut plus this term is less than or equal to 0. So they are less than or equal to 0. Hence I can say that the norm of ut is less than or equal to say minus 1 over theta. So if you say